Hello, and welcome to Sample Spaces and Events. My name is Tuesday J. Johnson. I'm a lecturer at the University of Texas El Paso and an assistant professor at Doña Ana Community College. Let's start with some definitions. Now, an experiment is an occurrence with a result or outcome that is uncertain before the experiment takes place. So, an experiment is not, hey, I wonder if I'm going to buy this when you're in line at the store. An experiment is maybe flipping a coin. Will it be heads or will it be tails? An experiment is not flipping a double-sided, wow, I can't even say that, a double-headed coin. You know it's heads on both sides. You know it's going to be heads. That's not an experiment. All right? The unknown, the uncertainty is important. The set of all possible outcomes is called a sample space for the experiment. For example, if you're flipping a coin, the sample space consists of heads or tails. Very rarely does a coin land on its edge without some kind of assistance. In a flat space, it almost never happens. Almost never happens. Given a sample space S, an event E is a subset of S. The outcomes in E are called the favorable outcomes. We say that E occurs in a particular experiment if that outcome of the experiment is one of the elements of E. That is, the outcome of the experiment is favorable. Maybe you're playing Monopoly. You don't want to land on Park Place, Luxury Tax, or Boardwalk because your friend has, well, the monopoly on that corner. So favorable outcomes are anything that doesn't land you on those three spaces. All right, so what is it you want to happen? Some examples. If we describe the sample space and list the elements of the event, 2 coins are tossed is our sample space. We want to find the sample space. Our event is the result is at most 1 tail. When 2 coins are tossed, we're going to assume that these are distinguishable. So maybe a quarter and a penny, you could tell them apart. If it's not otherwise stated, I always assume distinguishable. So they could both be heads. The quarter could be heads and the penny tails, or the quarter tails and the penny heads, or they could both be tails. The result is at most 1 tail. So my event, I want at most 1 tail. At most 1 means 1 or fewer, so 1 or 0. So I choose all of the elements of the subspace S that have 0 or 1 tail in them. And so all I left out was tails, tails. In the sample space, 3 coins are tossed. We could have a heads version of these 4. That takes us up to here. Or we could have a tail version of these 4. That takes, oh, I missed one. Look at that. 1, 2, 3, 4, 5, 6, 7. I missed one of the possibilities here. So we have heads, 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 tails, tails, heads, tails, tails. I missed tails, heads, heads. Right there. My bad. There should be 8. I missed tails, heads, heads. So if I want the result is at most 1 head, at most 1 head, at most 1, again, 1 or 0. So I take everything in here that has at most 1 head. So 1 head, HTT, 1 head, THT, 1 head, TTH, 0 heads, TTT. It turns out that I didn't miss this one in the event because it doesn't need to be there, but I did miss it in the sample space. Everybody makes mistakes. It's okay, own up. Describe the sample space and list the elements of 2 distinguishable dice are rolled. The numbers add up to 5. So my sample space consists of everything in this table, and here we have our cross-reference chart. It's a great way of looking at something like 2 dice are rolled. Adding up to 5, notice they're all here on the diagonal. So we have 1, 4, 2, 3, 3, 2, and 4, 1. The event space. Whereas if 2 indistinguishable dice are rolled, now what we're going to do is we're going to take out everything below the dotted line. Everything below the, not dotted line, below the bold line. Because indistinguishable, this is like Monopoly, right? Just 2 white die. It doesn't matter. Did we roll a 1-3 or a 3-1? They're the same thing. So our sample space is just the doubles here on the diagonal and everything above them. I could have taken below instead, but I chose everything above them. The event, one of the numbers is even and the other is odd. We often call this opposite parity. Opposite parity. One even, one odd. And we can see here 1 2, 1 4, 1 6, 2 5, 2 3, 3 4, 3 6, 4 5, 5 6. That's it. That's all of them. Once you have your sample space listed out, you just go back through and you describe all of them that show up. A letter is chosen at random from the word Mozart. Semicolon. The letter is a vowel. Don't overthink this one. What letters are in the word Mozart? M-O-Z-A-R-T. Which of those letters is a vowel? M's not, Z's not, R's not, T's not, it's only O and A. Do not overthink some of those problems. Now the complement of an event E is the set of outcomes that are not in E. For example, if your favorable outcomes are not landing on Park Place Luxury Tax or Boardwalk, then the complement is you landed on that and lost all your money. So the complement of E represents the event that E does not occur. I wasn't able to miss those 3 spots. The union of 2 events E and F is the set of all outcomes in E or F or both. I think of union as a marriage. All right, it's all of your stuff, it's all of their stuff, and it's all the stuff that you got while you were together. So a union, most frequently known union in the world, I would say, is marriage. All of your stuff, all of their stuff, all the stuff you accumulated together, that is a union. Whereas an intersection, that's like a first date. What do you have in common? What do you share? That's what you talk about on a first date, just kind of get to know each other. So the intersection of the events E and F is the set of all outcomes common to E and F. Thus E intersection F represents the event that both E and F occur. If E and F are events, they're disjoint or mutually exclusive if they have nothing in common. And if they have no outcomes in common, if you have nothing in common on a first date, don't make a second date. It's really not going to be worth your time. Just saying. Relationship advice from Tuesday Johnson. Alright, now the table shows the performance of a selection of 100 stocks after 1 year. We're going to take S to be the set of all stocks represented in the table. And I'm going to tell you right now, I did not come up with this problem. This is from Wayner Constantinople's 9th edition, I believe, Finite math text. I'm not sure about the edition, but they were definitely the authors. So we see here that the stocks either increased, were unchanged, or decreased at the end of the year. We looked at pharmaceutical, electronic, and internet stocks, and we have the totals here. We're going to use this table over and over again. We're going to use symbols to describe the event that a stock's value increased, but it was not an internet stock. So it's both of them, right? It increased, but it wasn't internet. So increased, we can see is represented by V. And at the same time, so intersected with not internet. Well, we know internet is I, so not internet, the complement would be I complement. Now, how many stocks increased, but not these ones, not the internet stocks? Well, there's 10 plus 5, or 15. So the number in the intersection of increasing stocks that were not internet is 15. An internet stock did not increase. So this time we want yes internet, but we want not increase. But we want them to be both internet and not increase. So internet intersected with V complement, so not increased. So we're looking at all the internet stocks, but not these ones. We're looking at 10 plus 15, so the number in the intersection of I and V complement is 25. We want to compute the number in P prime union N. What does this number represent? Well, let's break it apart. P prime, we find P, that's pharmaceuticals. So P prime, not pharmaceutical. N, not a pun, but close. N is unchanged. Union, that's all of this, all of that, or both. So the union are all stocks that are not pharmaceutical, or are unchanged, or both. And if we write that here, this should be in green. I don't know why it isn't. I'll just put a little green dot over it. the number in P prime, so not pharmaceuticals, unioned with unchanged, all right, and all the unchanged. We're going to look at not pharmaceuticals. So there were 50 pharmaceuticals. There are 50 others that are not pharmaceuticals. The number of stocks unchanged, or 40. The number in the intersection, not pharmaceutical, so these two, intersected unchanged. There were only 10 unchanged that were not pharmaceutical. So I counted those 10 twice. I counted them once in the not pharmaceutical, and I counted them once in the unchanged. So I have to subtract out one of those. 50 and 40 makes 90, minus 10 makes 80. Non-pharmaceutical stocks, or unchanged, or both. Slightly different here, the number in P union N complement. That's the number of stocks that were pharmaceutical, or they changed, right? Not unchanged, they changed, or both. So all the pharmaceutical is 50. All the unchanged, all the not unchanged, let me read that correctly, is 30 and 30, which makes 60. But how many of those did I count twice? I counted the pharmaceutical that increased, and I counted the pharmaceutical that decreased, both in pharmaceutical and in changed. So I subtract out those 20. 110 minus 20 makes 90. 90 of these 100 stocks were either pharmaceutical or they changed over the course of a year. Find all pairs of mutually exclusive events. That wasn't your eyes, I moved it. It cannot be a pharmacy and electronic stock at the same time. It cannot be pharmacy and internet stock. It cannot be electronic and internet. Similarly, my rows never intersect. So increased and unchanged, those are mutually exclusive. Increase and decrease, mutually exclusive. Unchanged and decrease, also mutually exclusive. So the columns are separate from each other, and the rows are separate from each other, all in pairs. So what does overlap? P overlaps V, P overlaps N, P overlaps D. E overlaps V, E overlaps N, E overlaps D, and similarly for I. So row and column show you intersections. Rows themselves, mutually exclusive. You can't be in one row and another row. But you could be in one row and a column, so these are not mutually exclusive events. Calculate the number in V intersect I divided by the number in I. V intersect I is 15. Divided by the number in I. All of I is 40. What is this? 15 40ths, if we divide both of them by 5, we get 3/8. This is the ratio of all increasing internet stocks to the internet stocks themselves. So all increasing internet stocks to all internet stocks themselves. So 3/8 of the internet stocks increased over this year. This is different. This is the number in decreasing internet stocks divided by the number of decreasing stocks. So decreasing internet stocks was 15. The total number of decreasing stocks was 30. Simplifies to 1/2. This tells us, because my denominator is decreasing stocks, this tells us that half of all the decreasing stocks came from the internet sector. A bag contains 6 gummy bears. Noel picks 4 at random. How many possible outcomes are there? If one of the gummy bears is raspberry, how many of these outcomes include the raspberry gummy bear? We're going to take this in a few steps. First, it's important to notice what we have and what we want. We have 6 gummy bears in our bag. We want 4 at random. So we have 6, we want 4. How many possible outcomes are there? Well, if we have 6 gummy bears and we want 4 gummy bears, we're grabbing at random. We use sets, therefore combinations. The combinations of 6 gummy bears where we want 4 at a time is 6 factorial over 4 factorial times 6 minus 4 factorial. And this 6 factorial, everything 4 and below will cancel out with my 4 factorial. Here I have 30 divided by 2, which is 15 different ways of grabbing 4 gummy bears from this package of 6. But if one of the gummy bears is raspberry, How many of these 15 different ways we could grab 4 include the raspberry gummy bear? Now this answer better be less than 15, because there's only 15 ways to do it overall with no preferences. We have 6 gummy bears, we want 4 overall. However, one's raspberry, so we want 3 other gummy bears. What we have is the combinations of the one raspberry that we have, we want it. And then, so multiplication principle, the combinations of the 5 other gummy bears left in the package, we want 3 of them. This 3 plus 1 makes our total of 4. The 5 plus 1 makes our total of 6. We have a total of 6 gummy bears. We want a total of 4 gummy bears. The combinations of one raspberry gummy bear taken one at a time is 1. The combination of 5 gummy bears taken 3 at a time, use your factorials, you'll find this is 10. 1 times 10 is 10. 10 different ways we could grab that one raspberry gummy bear in our group of 4 as we're eating this package. That should be it for sets and set operations. Thanks for listening.